Does anyone wants to record on their side? The lesson?
Yes, please, sir.
Yes, sir.
Is there a way to just click everyone to allow everyone to?
You sound record.
Okay. It's okay. I'm just trying to sort it out. Allow to. Okay, wait a moment. So I've allowed you to record, is that correct? Or I didn't allow you to record?
No, sir.
Yes, I'm recording. Thanks.
It's acting funny this
Oh
one.
wait, no, it's not. It just stopped. Like I can't record it. Still, I need permission.
Saying you need permission.
Yeah. So just again, right click and then allow.
Okay, just hold on. Let me stop recording. Sorry about that. So he said, Takuds, why I allowed you to record, huh?
Okay, now also record, sir.
Who else?
Brandon and Tandy, sir.
We can also. We're saying Brandon and Tandy allowed to record. Who else? Okay, that's fine. I'll also record you. Can you see my whiteboard? Not yet. You guys are quiet.
Not
No,
yet,
not
sir.
yet. Not yet.
Okay, can you now see my whiteboard?
Yes, yes, you can.
So we want to look at the reaction. Sarah, you're now there. Is she now there? Is Sarah there?
No, I don't think she's not here.
She is there. She joined.
She is.
Yes, I'm
here.
Tell your teacher that he needs to stick to his time. Because you
Yes, sir.
behind. Guys, you continue talking. Reaction kinematics, huh? As a topic. Reaction kinematics. So something is happening funny to my pen is not writing smoothly here. Anyway, it's fine. Reaction kinematics as a topic. So reaction kinematics is all about reactions, huh? It's all about reactions, how reactions happen. So we want to start with what is known as collision theory. What happens in reactions in chemistry? Collision theory. Sorry, I'm not sure what I'm thinking about. Collision theory. If I have A plus B reacting, giving me D as a product. So all I'm saying is I'm using A and B. So these are reactants. I'm sure you know that. They are reacting. Huh? So I said something happened funny to my pen. Then they are forming a what? A product. Huh? Reaction. So something funny might have happened to my pen here. It's not writing properly. Anyway, that's fine. To form products. Yeah, are you following me?
Yes.
So I'm just using A and B. They can be anything, whether it's whatever. We are reacting in chemistry to form that. So I'm just saying there's what we call a reaction theory. Huh? Then I want to explain how what we should know. Huh? So when particles, react. You can write that statement. My pen is acting funny. When particles react, or when particles react with each other. So in this case, it's A and B reacting with each other. They collide. When particles react, they collide against each other. Clear? When particles react, they collide, they bump into each other, they collide against each other. That's why it's called collision theory. They bump, they collide against each other. Clear? That's the first point.
Yes, sir.
Then only particles with sufficient energy. Let's write that down. Only particles with sufficient energy. Only particles with sufficient energy. Only particles with sufficient energy, clear? Will have successful collisions. Only particles with sufficient energy will produce successful collisions. Only particles with sufficient energy will produce successful collisions. I hope it's making sense here. Okay, let me just bring it. If I was reacting sodium here with chlorine, from chemistry, you know that this sodium element is made up of millions of what? Of atoms. Clear? This chlorine also is also made of many atoms. But we are saying when these atoms collide, it's only those that have got enough energy that will produce a successful collision. Clear? Is that clear, the first point? So I'm saying when these atoms collide, it's only those with sufficient energy that will produce a successful reaction. Successful collision means successful reaction. Clear? Those without, the next point, those without sufficient energy will simply bounce back. Those without sufficient energy will simply bounce back. Clear? Those without sufficient energy will simply bounce back. Hope it's making sense here. So if I have a, yes, you've got a question there, or you missed something, or you're saying yes, sir. So if I've got a graph like this, I'll explain the graph. You don't have to know it. It's more of A level, but I'm saying I'm using it to explain. So if I have a graph like this, so this is showing you energy, your particles. So you find that this one here, this peak here, shows you that's where you have the average energy for particles. But this small part here that I'm shading here is only, that's what we call activation energy. So activation energy is when particles have got sufficient energy for a reaction. So it's only this small section where we are having successful reaction. Everything before that will not have successful reactions. So in general, it's only a few particles. You can write that in general, it's only a few particles that will have sufficient energy for a reaction to take place. Clear? In general, it's only a few particles that will have sufficient energy for a reaction to take place. And we call that activation energy. And we call that activation energy. Are we together? Collision
Yes.
theory. I've explained it properly. So now let's look at factors that affect a chemical reaction. Then we see now how we apply whatever we just talked about now. Factors that affect a chemical reaction. What are the factors? Let's list them. What are the factors in general? You have learned them. Factors that affect a chemical reaction. What did you say? Temperature.
Temperature.
Yes. Number one, temperature. Correct. What else? Chemical reaction is affected by temperature. What else affects a chemical reaction? Think in chemistry.
Catalyst.
A catalyst. Correct. Yes. Catalysts. You know that from biology. Surface area, correct. What else? Surface area
Concentration.
applies to what? You can write in brackets applies to
Concentration.
solids. Huh? Clear. For concentration, does concentration apply to solids? No, it applies to liquids. Concentration. So this one applies to liquids. Talk of concentration, don't talk of solids. Huh? We talk of liquids. Clear. So those are the four from your syllabus: temperature, catalysts, surface area, and concentration.
Sure.
Let's start with temperature. Who can explain how does temperature affect a rate of reaction? Temperature. How does temperature affect a rate of reaction? What's the next lesson after this one? Go
Geo.
Geography.
Geo.
Geo today. Do you have a break in between or you don't have a... Oh, it's Geo. Up to half 1 hour. Correct. 1 hour.
Yeah, no break.
Yes, that's good. Okay, sorry. Can someone explain to me, Tandy, what do you think? Temperature. If a question says explain how temperature affects speed of reaction, 3 marks, what are you going to say?
When there's an increase in temperature, the particles gain kinetic energy to perform the reaction.
Let's go back. You've got a point here. Remember, I wrote A plus B here. I was explaining something to do. I want you to explain in terms of collisions. Your first part was very correct. If I increase temperature, A and B are going to gain kinetic energy. Clear? The particles gain kinetic energy. So if they gain kinetic energy, what does that mean in terms of collisions? It increases the frequency of what? Of collisions. Huh? So when particles gain, when temperature is increased, the particles gain kinetic energy. When they gain the reactants, in this case, let's talk of reactants. So we can write that when temperature is increased, you can write that down, summarize it down. When temperature is increased, the reactants gain kinetic energy, like what she said, comma. When they gain kinetic energy, it means the frequency of collisions, because they're going to bump more, yeah, the frequency of collisions. For example, if before, don't write this down, if they were like, let's say in general, there were like 50 collisions in a minute. When we increase temperature, maybe they're going to be 200 collisions. That's what I mean. Huh? So the frequency of collisions increases. Clear? Are we together? The frequency of collisions increases. Now, if the frequency of collisions increases, it means now it increases the chance or the probability of successful collisions. Is that making sense?
Yes, sir.
Let me take you back. Remember, before increasing temperature, we said when particles collide, only a few have got sufficient energy. Huh? Clear. But now we're saying when we increase temperature, number one, we are giving them more kinetic energy. Number two, when you increase more kinetic energy, it means there's more collisions. not only are there more collisions, because we have increased kinetic energy, we are going to have a high chance or a higher probability of successful collisions. I hope you summarized that correctly. Yeah? So number one, we said when particles collide, when temperatures increase, particles gain kinetic energy, then that increases the frequency of collisions. And not only does that increase the frequency of collision, it increases the chance or the probability of successful collisions. So in summary, temperature increases the speed of a reaction. I hope it's clear to everyone there. In summary, temperature increases the speed of a reaction. Now, what you need to know now is to know the graphs. Because they will ask you which graph, where was temperature increased, and which graph was at a low temperature. So rates, so these graphs are the same for all the four rates of reaction. Clear? Then you have something. Then this is obviously your timer. Then I'll have something. Let me draw something like this. So this is my curve C, and this is my curve A. My question now is which one is at a higher temperature, A or C? And I want to see your result. C. Very correct. Huh? Why? Because when this becomes flat like this, it means the reaction has stopped. Where has this reaction stopped? Somewhere there. This reaction, when it becomes this way, the reaction is stopped here. This one takes long. The reaction only stops where? There. Hope it's making sense there. So C is at a higher temperature than reaction A, because C takes short time for the reaction to complete. Are we together there?
Yes, sir.
Yes, sir.
Okay, I hope it's clear with everyone there. Now, let's talk of surface area. Surface area. How does surface area, we said it applies to solids, huh? So how does it affect the rate of reaction?
I think by having finer powders, this will increase the speed of reactions.
No, remember we're not talking of finer, I get your point. But what you're simply supposed to talk of, you're supposed to talk of a large surface.
With a large surface area, won't the reaction be slower? Because when the surface area is small, the concentration is higher, meaning that
Don't talk of concentration here. We're talking of, don't combine the two, because we're talking of solids here. So surface area, nothing to do with. She was correct to say fine powder, but I was correcting her. She should not mention that. She should simply mention surface area. So a larger surface area, right, that in general, a larger surface area means increases the rate of reaction. Clear? I'll explain that now. A larger surface area means the rate of reaction is increased. Huh? A smaller surface area, you reduce rate of reaction. Clear? Then I'll explain here. If we use calcium here, don't write it down, I just want to illustrate something. Calcium marbles in a labor. So if you use this big calcium like this, then if we've got a crushed calcium, we've got these small ones, or like fine powder, clear. So fine powder here, it means large surface area of your calcium. Let's say I'm going to react calcium maybe with hydrochloric acid, but I'm using calcium fine powder, and I'm using these stones, calcium, whatever there. So now, if I go back to what you wanted, why you got confused here. If this is fine here, I have so many atoms of calcium that are exposed to this hydrochloric acid than when it's a lump like this. Is that clear? So it means when it's fine powder, it's a large surface area.
Already getting homework.
Are we together? So if it's a lump like this, it means it's a small surface area. Are we together? Is that clear with everyone there?
Yes.
I was explaining this. So it means by increasing the surface area, more particles, you can write that increasing the surface area, more particles of the solid are exposed. More particles of the solid are exposed to the other reactant. Clear? More particles of the solid are exposed to the other reactant. So it means there's a higher chance of success. It increases the chance of successful collisions. Clear?
Yes,
So
sir.
the graph will be just the same. I'm not going to draw it will be the same graph. Because I can draw the same graph and ask which one was fine powder, which one was what. But they will be like the same graphs. Huh? I'm simply applying the same concept. Huh? Where I say the way this is fast, so it's fine powder, and this is what? This is small surface area. I hope it's making sense. Huh? So,
Yes, sir.
so surface area is only to deal with solids. Now, if it was like a proper lab session, huh, and I want to do an experiment to compare what I've just said, I can use calcium carbonate. Calcium carbonate, if you burn it, if you add hydrochloric acid, it produces carbon dioxide. Huh? But now you have to close this and have an opening there. This is closed with a cotton or whatever. So that the carbon dioxide here, because remember what you are doing is you measure the same amount. Huh? If you are using fine powder of calcium, then if you are using the marbles there, this will be maybe like, for example, if say 100 grams, this has to be exactly 100 grams, clear. So that if the experiment is fair, I use the same amount. Huh? Then the acid that I'm adding, I also use same amount, clear. What I simply measure, because I know that if I add an acid to a carbonate, carbon dioxide is produced. I'm measuring the rate. I'm measuring the volume of carbon dioxide produced every minute. And your fine powder expect to produce more volume of carbon dioxide per minute. Clear? Is that making sense?
Yes, sir.
Now, let's talk of, so we've talked about surface area. What else did we talk about? Catalyst. How does a catalyst affect? Catalyst? Who knows? How does a catalyst affect a chemical reaction? So you can write that a catalyst reduces the activation energy. Remember I talked about the energy that you need for successful collision. So it reduces, a catalyst is the only one that reduces, you can write that the catalyst is the only one that reduces the activation energy for the reactants, thereby providing an easy pathway for the reactants. So if it reduces the activation energy, it means it increases the chance of successful collisions. Are we together? Making sense? A catalyst,
Yes,
we said it reduces your activation energy. So if they reduce the activation energy, it increases the chance of successful collisions. That's how a catalyst works. That's how a catalyst speeds up a chemical reaction. Now the last one is concentration. So by the way, you're going to have a chemistry on the first day, chemistry homework. That one I won't forget. So concentration. We talked of liquids, huh? Concentration. Concentration, for example, if I say 10 moles per cubic decimeter, per liter per cubic decimeter, if I say 0.5, it means this one has got a higher concentration because it's the same volume than this one. Clear? So higher concentration, with higher concentration, it means more particles per unit volume. A higher concentration means more particles per unit volume. So if there is more particles per unit volume, you are increasing the chances of successful collisions. Are we together? So higher concentration increases the speed of. So the higher concentration, it means higher rate of reaction, huh? Not speed, higher rate of reaction. Clear?
Yes, sir.
Now I think it's time for Geo. So you definitely get a chemistry, but it's a multiple choice. That's a good thing about today's homework thing. So let's switch on to Geo. Those that don't Geo, we'll see you tomorrow.